For the most part, we use private IP addresses in our networks. But the internet uses public addresses. So how do we make these two work together? We need a device to translate between these two types of addresses. And for that, we have Network Address Translation, or NAT. Let's see how this works and how it's configured. Think of the header on a packet. This contains the source IP address that the packet was sent from, as well as the destination IP address that the packet is being sent to. NAT is the technology that can take an IP address in a packet's header and replace it with a different IP address. The most common use for NAT, as mentioned at the beginning of this video, is to translate between public and private IP addresses. This is part of a strategy to save public IP addresses across the globe. Decades ago, the intention was that every device would have a public IP address. However, there's a limited number of public IP addresses available, and we started using them far too quickly. So these days, we mostly all use the same private ranges in our networks. But to connect to the internet, we need public addressing. So a router between our network and the internet will translate private IPs to public IPs and back again. And if you're wondering, we will generally have public IP addresses given to us by our internet provider, and they often won't give us very many. How does this work? It's all based on the IP header. Every packet has this header, which contains a source address and a destination address. A router has a set of rules about which traffic should be translated and which traffic should be left alone. When a packet arrives at a router, the router will examine the IPs in the header to find traffic that matches a NAT rule. If a packet matches a rule, then this router will rewrite the source or destination IP address in the header and send the packet on its way. We can even configure NAT to change port numbers in a TCP or UDP header if we want to, but we'll save that one for later. There are two types of NAT. These are source NAT and destination NAT. Source NAT is the most commonly used type of NAT. As the name suggests, source NAT changes the packet's source IP address. This is generally used for internet access, as we explained earlier, where we are using private IP addresses in our network. The router takes the private IP in the header and replaces it with a public IP. Devices on the internet see this packet as coming from a public IP, and they are able to send traffic back. The router will change the IP address back to a private one as the packet passes through. The alternative is destination NAT, which is a bit less common. As you've already guessed, this is where the router changes the destination IP address rather than the source IP. We might use this if two organizations have merged and they were already using the same IP space. Normally this wouldn't work as they need to have unique IPs. However, we could use NAT so each network thinks that the other is unique. This scenario is a bit complicated, so we'll leave this one alone. Some devices can translate both the source and the destination IPs. This is typically the role of a firewall which has advanced NAT features. We do have a video on configuring NAT on the ASA firewall if you'd like to see that in action. It's a bit more complicated though, but it's worth a look if you're interested. But in this video, we're only going to look at source NAT for internet access. Before we get right into the configuration, there's a couple of terms to understand. When we configure the router, we specify which interfaces are inside our network and which are outside. Cisco uses the terms local and global to describe the inside and outside. Keep in mind that different vendors will use different terms for this. When a device first creates a packet, it puts its own IP address in the header as the source. This IP address is called the inside local address. This is the real IP of the host inside your network, and it is probably a private IP. The outside IP is the destination address. This is the IP of a device outside of our network. Technically, this may not be the destination's real host IP, as NAT may change it, but this is what our hosts think is the real IP. After a packet has a NAT rule applied, different terms are used. The source IP address is called the inside global address. This is our host's IP address after it has been translated. For internet access, this is now likely a public IP. The outside global IP is still the destination address. This would only change if we configured destination NAT, which is not the case in this example. As usual, there will be some quiz questions throughout this video that you can come back to later to test your understanding. We're now going to look at configuring static NAT, also known as one-to-one NAT or basic NAT. A static NAT will take a local IP address and statically map it to a global IP address. These two IPs are always a pair, and the mapping does not change. We would typically use this if we had a server on our network, maybe a web server, that we want to make available over the internet. People on the internet can then access our web content using the public IP that we configure in the static NAT. The downside to static NAT is that we use up public IP addresses very quickly, as we need a public IP for every static NAT rule. We're going to use this topology to configure several types of NAT in this video. You'll notice that there are three areas: the LAN, where our workstations are, the DMZ, where our web server lives, and the internet. We're going to start with a static NAT, so our web server can access the internet, and so people on the internet can access our server. To start with, there's no connectivity from our server to the internet. This is because the ISP does not have a route in place for our private address ranges. To mimic what this would be like in the real world, we will not touch the configuration of the ISP's router. The first step is to get on our gateway router and define which interfaces connect to the inside and which connect to the outside of our network. We can use the IPNAT inside and IPNAT outside commands to achieve this. But notice that as soon as we enter the first NAT command, the router creates a special interface called NVI0. This is a virtual interface that optionally allows us to configure NAT in a very different way. We're going to stick with the traditional NAT configuration in this video, as I think it's easier to learn. I'll include a link in the description if you want to know more about this special interface. The next step is to configure NAT itself. The inside keyword can be a bit confusing, but it basically means that we're configuring this NAT from the perspective of traffic passing from the inside of our network to the outside. We'll talk more about this soon. Source refers to this being a source NAT. Static means we're configuring a static NAT rule. We'll look at dynamic soon too. Next, we give our router the inside local IP of our server. That's the server's real IP address. And finally, the inside global IP, which is the server's public IP. If we go back to our server and try that ping again, we'll now see that it's working as we would expect. Back on the gateway router, we can verify this with the show IP NAT translations command. This shows us the inside and outside IPs for each translation. At the bottom, we can see the static NAT that we configured. This will always be here as it's, well, static. The top entry is an example of how the router tracks each translation. This is the ping we just ran. This will age out over time and will be removed from the list. And just to confirm, if we connect to the server that's on the internet, we can ping our server's public IP. What we've just seen here is an example of bidirectional NAT. When we think of NAT, we often need to think about where the traffic is initiated, that is, where traffic starts. For example, traffic may start on a workstation with a web server on the internet as the destination. The web server will then send traffic back to the workstation. This means that NAT is applied in a particular direction, and that direction depends on where the traffic starts. Consider the example we just configured. There is a web server inside our network, and people outside our network need to reach it. The server can initiate a connection to the internet if it needs to, or something on the internet can initiate a connection to the server. The NAT we configured will work, no matter which direction the traffic is going. This is a bidirectional NAT. The opposite of this is called unidirectional NAT, which we'll see at the end of the video. But for now, let's consider how to configure NAT for our workstations. Usually we won't use a static NAT for this, as we have a lot of workstations and not many public IPs. One option we could consider is dynamic NAT. This does not use a one-to-one mapping between a private IP and a public IP. Instead, we can create a pool of public IP addresses and let the router map an IP to each workstation as they're needed. Just as before, we need to consider which interfaces are inside and which are outside. Our outside interface is already configured, we just need to add GI0/2 as another inside interface. Notice that we can have more than one interface configured as inside or outside. There's a bit more work to configure a dynamic NAT. One thing we have to do is define a NAT pool. This is our group of public IPs. Most of this is self-explanatory. Pool tells the router that we're configuring a pool of IP addresses, and public pool is the name of our pool. 203.0.113.100 is the first IP in our pool, and .110 is the last IP. Netmask is the subnet mask that goes along with the IPs in this range. The next part is an access control list, or ACL. We've used these before to allow or block traffic, but ACLs can be used for far more. The real purpose of an ACL is to identify interesting traffic. We do this to define which traffic should have NAT applied to it. So in our case, interesting traffic is any IP address in the workstation subnet. To do this, we've created an extended ACL called workstations. We could use standard ACLs and numbered ACLs, but I prefer named extended ACL as it makes a bit more sense when reading through the config. We then use a permit statement to match anything coming from the 192.168.0.0 network with any destination. You'll also notice that we've used a wildcard mask for matching traffic. Check out the ACL video if you want a refresher on wildcard masks. For interest's sake, what do you think will happen if we added the deny statements along with the permit statement? Deny will simply tell the router not to match that traffic. It won't block anything though. We might use this if we wanted to match all traffic from 192.168.0.0 except for one or two IPs. This might be something you can try for yourself in a lab. And finally, we tie all our components together by mapping the private IPs that we matched with the ACL to the public IPs listed in our pool. This command is very similar to the static NAT command. The main differences are the list and pool keywords. Heading over to our workstation, we can use ping to confirm that this is working. And just like before, we can see the results of our ping and see that our workstation 192.168.0.1 has been mapped to 203.0.113.100. We can dig up a bit more information with show IP NAT statistics. We can see which interfaces have been configured as inside and outside interfaces. We can see the pool that we configured, as well as how many IPs have been allocated. And we can see hits and misses. A hit is whenever the router needs to look for a NAT mapping for a packet and successfully finds one in the translation table. A miss sounds like an error, but it actually isn't. This simply happens when the router looks up the NAT table, finds there isn't already a translation in place, and then needs to create one. Closely working hand in hand with NAT is port address translation, or PAT. In fact, they're so closely related, we usually just use the term NAT as an umbrella for both of these technologies. If you remember back to when we looked at TCP and UDP, you will remember that they also use headers. And in these headers are source and destination ports. Just as NAT rewrites IP addresses in the IP header, PAT rewrites port numbers in a TCP or UDP header. In most cases, PAT and NAT will work together, so one will be changing the IP address and one will be changing the port number. This is quite common when we want to make a few services available to the internet by port number alone, rather than translating the entire IP address, which exposes all of a server's ports to the internet. We're going to see a particular PAT feature in the lab now called port forwarding. We're going to get our server on the internet again, but this time it's only the web service on port 80. Behind the scenes, I have reset this lab to default, so we no longer have the static and dynamic NATs that we configured earlier. Of course, members can download both of these labs from the website. Because I reset the lab, we need to go back and configure the inside and outside interfaces again. Simple PAT configuration is very much like configuring a static NAT. We've only added in some port numbers as well as a TCP keyword. TCP, of course, is the protocol that we're using, with UDP as the alternative. The first port is the real one on the server, and the second port is the translated port. But wait, aren't those two ports the same? What's the point of doing this if we're not actually changing anything? In this case, we're forwarding a single port from the internet to our server, just port 80 with no other ports. So how is this different to the static NAT that we configured earlier? The static NAT is not concerned with ports at all. When we configure a static NAT rule, we're telling the router to make all ports on the server available to the internet. What we've done here is created an IP translation that only works for port 80, but we definitely could have translated from port 80 to some other port if we wanted to. To see this working, we can jump onto the server on the internet, and we can use the Linux command curl to connect to our web server. This command uses HTTP to download a web page if there is one available, and we can see that this is working. But what if we try the same thing on a different port like 443? This simply doesn't work as NAT has not been configured to forward port 443 to the server. But one last thought. What if we try pinging from our server to the internet? This fails. Once again, we have no NAT rules to translate this traffic for us, so ping will not work. Before we move on, here's a couple more questions to get you thinking. There is one more technology we need to discuss, which some may consider the most important of them all. This one is called port overloading, or masquerading, or many-to-one NAT. Think of a case where we don't have many public IP addresses available to us. Maybe we've only been given one or two by our service provider. In a case like this, we can't use a dynamic NAT pool like we did earlier. This is because dynamic NAT will map one public IP to each host that needs internet access. We'll very quickly exhaust the pool of IPs, and any additional traffic will be dropped. So it's clear we need an alternative. This is where port overloading comes in. This is still a form of dynamic NAT and PAT, but the router will translate ports as well as IPs. In addition to the pool of IPs, the router has a pool of ports that belong to each IP address. There are about 64,000 ports in each pool. Now think of the first workstation accessing the internet. It sends a packet to the router, which contains the source and destination IP and port numbers. The router will rewrite the source IP with the public IP address, and it will also rewrite the source port with a port from the pool. The router keeps track of which ports have been used and which workstation is using them. This way it knows where to send return traffic. Now when the workstation wants to access the internet, it goes through the same process as before. In our example, it gets the exact same public IP as the first workstation, but it will get a different source port from the pool. In this way, devices on our network can share a single public IP address as they each use unique source ports for each connection they open. And as there are about 64,000 TCP ports and 64,000 UDP ports, we won't run out of ports quickly. Before we move on to configuring this in the lab, see if you can work out the answers to these questions. Right, so port overload is not too hard to configure. Our inside and outside interfaces are already defined, so we won't need to worry about them at this time. First, we'll create an ACL to identify traffic from our workstation subnet. This is the exact same ACL we configured earlier. Next, we create a pool of public IPs. This is nearly the same, but this time we've only put a single IP in there. And finally, we create our NAT rule. There's really only one new item here, which is the overload keyword at the end. This statement overloads more than one inside IP address onto the single public IP address. As usual, we'll confirm this is working by running a ping from the workstation, which is working just fine. And of course, we can confirm this with the show IP NAT translations and show IP NAT statistics command. From here though, I would recommend that you try this yourself in the lab and test it out with a few workstations rather than just one. And of course, here are two final questions to test yourself out with. Earlier we spoke about bidirectional NAT, where traffic can be initiated from either the inside or outside of our network. Port overloading behaves differently. This is an example of unidirectional NAT, where traffic must be initiated from inside of the network. Return traffic is fine, of course, but the connection needs to start on the inside. Why is this? Because the router builds its table of port to IP mappings dynamically as connections are needed. So if someone tries to connect to a workstation from the internet on a particular port, it's highly likely that that port is not already in the translation table. This concept is a bit complicated, but the key point is this. For unidirectional NAT, the initial connection will only work in one direction. In a nutshell, a router configured with NAT can rewrite IP addresses and ports in the header of a packet, typically for internet access. If you'd like to see some more advanced examples of NAT, take a look at the ASA NAT video on this channel.